Chapter 16 of SDM4 is the last of the probability chapters, the last part of this part of the book, and it really introduces probability models in more specific detail. We think about the idea of what we call Bernoulli Trials in terms of a single event that may occur. There are kind of four ways we think about that coming together. Different from the idea of the geometric model, where we actually don't have a fixed number of trials, but we wait for something to happen, where it's always going to have the same probability. We think about some different ways of approaching these and some of the conditions that are going to be necessary for it. The binomial model is just a generalization of the Bernoulli model. The Bernoulli model is just a single trial. The binomial allows us to have multiple trials. And then kind of thinking about how some of these calculations can come together and how we can work with the binomial. It actually describes the expected value and standard deviation. So while it's true that there's ways to approximate the binomial with the normal model, and it's what your parents would have done in terms of their teaching of statistics, it's not something we need to do anymore, and we'll see that in the SDM4 and R. And so this idea of when it's going to be approximately normal works reasonably well, but as I said, it's a little bit old school. We're going to be using other kinds of approaches. In the same way, the continuity correction was needed back before computers could actually do computation, so you're not responsible for the continuity correction. The Poisson model is a lovely thing, but it's again beyond the scope of this course. It's a kind of a model for counts that's commonly used. And then some other continuous random variables. We'll see a little bit more briefly in the course, uniform and the exponential. We're going to be doing a little bit of work with these, but not so much. Just want to give some other examples. So what can go wrong? Oftentimes people confuse the Bernoulli and geometric. That you need to have sufficient n to use the normal approximation. As I said, we're not going to need that as much. And it's important to assume that not everything is normal. And here's a good example when we think about these CEO salaries. How do we do this in R? So there's a couple of things going on that you'll want to keep in mind. In the same way that we had before D norm and P norm and Q norm, these are functions that actually calculate important aspects of normal distributions. We have D binom, D geom as a way of kind of calculating particular probabilities. The geometric model examples on 16.2 can be verified. We can use the plot dist function as a way to generate the distribution, what that looks like for different things, and verify each of the values for the think, show, and tell. Similarly, for the binomial, we can use the binomial function, and we can sample in this case from a whole bunch of binomials to see what's going on for the BSPAM example later on in the book. The normal approximation of the binomial, as I said, it actually works fairly effectively. For large stuff, we won't need it as much. Your parents had to use this. The good news is you don't have to. Continuity correction, again, you're not responsible for. Poisson actually looks fairly much like a normal, and there is a kind of an equivalent approximation of the Poisson. We can use the R-unif function to generate random uniforms and plot exp or plot dist for the exp function as a way of looking at exponential ranges. So this chapter, Last in Probability, sets out some important probability distributions. We're going to be focusing for the most part on the geometric and the binomial, the Bernoulli, just a special case of it, and occasionally the uniform and the exponential.